Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we're going to learn about dynamic programming. Developers often view dynamic programming as one of the most intimidating topics. I know that's how I felt early on, and they fear practicing this topic the most when studying for their coding interviews. However, we'll see in this lesson and the entire dynamic programming module that it's a concept that anyone can learn and understand. We're going to break down and simplify the concepts and explain what's happening in plain English. In fact, if you've been following the course in order, we've actually already learned all the concepts required for dynamic programming, and we won't be teaching anything new here in this lesson. I'll just be showing you the big picture and how all the pieces fit together to form dynamic programming. While dynamic programming is much less intimidating than people believe, it is a topic that just takes practice. But once you work through all the lessons and interview questions on the subject in this course, I know you're going to be confident going into your coding interviews and feel completely prepared to answer any dynamic programming question that you're given. So what is dynamic programming? Dynamic programming is just an optimization technique. And what you do is use a data structure to store or memoize the steps as we build up the solution algorithm. So we're just using a data structure to store expensive calculations and remove duplicate work. The foundation of dynamic programming is really two concepts we've already discussed, and that's memoization and overlapping subproblems. Memoization is where we store the result of expensive function calls, so we only perform the calculations once for any given input. A subproblem means we can solve the overall problem by breaking it into smaller increments of repeated function calls. So the subproblem means we solve the same logic over and over, but use multiple input values, which creates different results for each subproblem. And then, by combining the results of all the subproblems, we can calculate the overall solution. An overlapping subproblem means the solution tries to solve the same subproblem more than once, which means we call the subproblem function multiple times with identical input values. Doing this creates duplicate work since we've already calculated the solution for the subproblem for this same input previously. So we've been told dynamic programming is an optimization, and the optimization works by using memoization to store the results from overlapping subproblems. Then, when we try to solve the same overlapping subproblem more than once, which means we're using the same input, we just return the memoized version instead of performing the calculations again, and this removes the duplicate work. And by removing this duplicate work, this is how we get the optimization of dynamic programming. And this can be used both with top-down and bottom-up solutions. So with dynamic programming, we break the problem into smaller subproblems, and each of these subproblems uses the same logic to find the solution. So we use the same code to find the answer to each one. The only thing that changes is the input value and then the answer to previously calculated subproblems. And then, once we find the answers to all the subproblems, that's going to be the overall answer to the question. And as we work through the subproblems, we store the solution to each one in a data structure. Here we're using a hash table. But when you have these sequential integers, it also works very well with an array, so it's very common to see both of those data structures used with dynamic programming. So let's visualize how this works. You start by solving each problem one at a time, and then you move forward and use the previously calculated answers and the new input values to find the solutions. After you calculate each answer, you take that solution and store it in the data structure. So each subproblem is its own decision. And then to solve the subproblem, make the optimal decision at each point to find the best answer. So you take the input value for this subproblem, and then you use the solution from previously calculated subproblems, and then find the best choice at this moment. And then once you make this decision, you move on. So we're solving these subproblems one at a time locally, and finding the best choice, and then building up the solution until we get to the final spot or the last subproblem, and then when we solve this, it's the overall solution to the problem. And the last answer to the subproblem is also going to correspond to the last item in the memoization data structure, so we return the last item, and that's the solution as well. So finding each solution locally allows us to find the solution globally once we combine all the answers, or use the previously calculated value to answer each subproblem. And we know these subproblems can be overlapping, so not only do we use a previous value, but we might use many previous values multiple times to calculate each subproblem solution. And we know this works both with bottom-up and top-down algorithms. With bottom-up, we just start at the beginning, and then solve each subproblem one at a time, and move on. So we start at the smallest value, and then work up to the largest value, which is the solution. And as we work through, we just store each solution in the data structure, and then the key is the input function value for that subproblem, and the value for that key is the solution. And then, as we build up the solutions, we look backwards, or take the values from previous subproblems to calculate each additional subproblem. And then the logic for top-down is very similar. We just start at the top or the final spot, and then express the solution recursively. So each of these recursive functions is just an answer to a subproblem, and we reduce the input value each time until we get to the base case, or the smallest value, which is where the bottom-up approach started. At the base case in top-down, this is where we return a constant value, and then this allows us to start building up the solution. So then it starts to look very similar to the bottom-up at this point, because we're just solving each subproblem one at a time, but then when we solve a subproblem, we again store it in the memoization data structure. So then, if we call a recursive function with the same input again, instead of recursing backwards, we just return the value immediately and then continue on. So we remove all that duplicate work, both in the bottom-up and top-down, by calculating each problem once, and then just accessing the value in the hash table each time. And now let's look at the keys to dynamic programming. The first is that there are subproblems. So we can find the solution to the question by solving the same smaller problem repeatedly with different input values, and then combine these solutions to find the overall answer. The second key is that the subproblems are overlapping. This happens when the solution algorithm requires the result from the same subproblem multiple times, which means the subproblem is being called with the same input more than once. Finding the same solution repeatedly creates duplicate and unnecessary work. And the final key is that we can memoize the results of overlapping subproblems to remove the duplicate work. After we calculate the solution for a subproblem for any given input, we store this value in the memoization data structure, and then when we try to use the same input or try to solve the same subproblem again, we can just return that solution immediately from this data structure instead of needing to perform the duplicate work from the overlapping subproblem. So dynamic programming often means calculating all the values for all the steps to reach the desired solution. And this is sometimes a mental hurdle for developers to get over when they're first learning dynamic programming. It can sound inefficient to calculate all these values, but oftentimes this is just the only way to solve the problem. But the way we optimize and improve on it is by using memoization to store the results from the subproblems, so we only perform calculations once and remove duplicate work. Top-down Fibonacci is a great place to start thinking in dynamic programming and understanding how it works. So let's go through it step by step so we can really see what's happening. we know the subproblems for Fibonacci is that any given Fibonacci number is the sum of the two prior Fibonacci numbers in the sequence. So to find the 7th Fibonacci number, we sum the 6th Fibonacci number plus the 5th Fibonacci number. But when we're solving this top-down, we don't immediately know these numbers, so we must continue to recursively find each answer until we hit the base cases. Then once we hit the base cases, we can begin building up the solution. The challenge with Fibonacci, we know we have overlapping subproblems. Multiple Fibonacci numbers use the same Fibonacci number to find their answer. But then, when we call this recursively, it spawns all these additional calls that all require the same Fibonacci number because we're calculating all of them down to the base case. In a brute force solution, we can see that 2 is used multiple times, 3 is used multiple times, 4 is used multiple times, 5 is used twice, so we have the same numbers appearing many times. These are the overlapping subproblems. And this causes a brute force solution to operate in O of the 2 raised to the n power. So the brute force solution is very inefficient. But with dynamic programming, after we calculate the solution to a subproblem, we can store it in a data structure, and then anytime we need this number, we can access it from the data structure instead of performing all these calculations. So the first time we calculate 2, we store the value 1. The first time we calculate 3, we store the value 2. When we calculate 4, we store 3. When we calculate 5, we store 5. When we calculate 6, we store 8. And then finally, we calculate 7, which is 13 and the answer. So the benefit of this is after we memoize it, after the first time we calculate it, when we need the solution to this subproblem again, we just return the value that we already calculated. And we see that this happens each time that we need the solution to a subproblem that we've already solved. And not only can we return immediately, but then it prevents all these additional recursive calls and allows the algorithm to operate much faster. So in this case, we used a hash table. We know that 0 and 1 are already 0 and 1, so we initialize those in the hash table. Then when we calculate 2, we store the value of 1 for that input in the hash table. When we calculate 3, for the key 3, we store the value 2. Then for 4, we store the value 3. For 5, we store 5. For 6, we store 8. And then finally, when we get to 7, we store 13, but then return that as the answer. So we remove all these additional calls by using this hash table to memoize solutions, and this optimizes the top-down Fibonacci solution to run in O of n linear time. So on the right, we have the brute force recursive top-down Fibonacci function, where to find any Fibonacci number, we just find the two numbers before it, and then we sum those together and return that value. By needing to find two numbers below it, or recursively calling this function twice, we get those overlapping subproblems. Different Fibonacci numbers require the same Fibonacci number prior in the sequence to calculate their value. And then when you call this recursively, it spawns many recursive calls where we see the same Fibonacci number being calculated multiple times in its subproblem, because we continue to build downward to the base case, so we enter these lower Fibonacci numbers many times. We could see this visually in the recursive tree from all that branching and spreading outward and downward. But then to optimize the solution, we initialize a memoization hash table. Then, after we calculate any Fibonacci number, which we represent by n from the input, we store this Fibonacci number in the hash table. So for the value of n, or the input value, this is the item in the Fibonacci sequence, and this is the number that corresponds to it. And then to return early and remove that duplicate work, we have a simple if statement where we check if the value exists in the hash table, and if it does exist in the hash table, we simply return it. So we only enter this recursive case for the first time that we try to calculate any value of n. Then on any subsequent calls, we simply return early. And now let's see how dynamic programming works with a bottom-up solution. We're going to find the 7th Fibonacci number using a bottom-up approach. Again, we use a hash table, and the key is the item in the sequence, and we go from 0 all the way up to 7, which is the number we want to find. And then the value for that key is the Fibonacci number. We initialize 0 and 1 to the values 0 and 1 because these are the first two numbers in the Fibonacci sequence. Then to find any given Fibonacci number, it's simply the sum of the two prior numbers in the sequence. So for example, memo of 2 is going to be memo of 1 plus memo of 0. And then we continue to build up the solution along the way, where we calculate any given number by summing the two prior numbers in the sequence or using the solution from those numbers' subproblems. So let's walk through that now. So to find each number, we just use the two prior numbers in the sequence. So 2 was the sum of the 0 and 1, then 3 was the sum of 1 and 2, 4 was the sum of 2 and 3, 5 was the sum of 3 and 4. So we just continue to use the solution to previous subproblems to find the current value all the way up to the solution we want, which is 7. So let's view that in code. We initialize the hash table. Then we have this first if statement, so if we ever call this function again and we've calculated a value, we can return. Then, since we have the first two Fibonacci numbers, we start at 2 and we iterate to n. The current Fibonacci number is just the sum of the prior two, and then we store that value in the memoization hash table. Once we're done, we've calculated the nth Fibonacci number and can return that value as the solution. So each iteration in the loop is a subproblem, and we solve that subproblem or find the solution to it by using the answer to previous subproblems to find the answer to the current subproblem. And it's worth noting that that data structure, the hash table that we've been using, isn't strictly required in a bottom-up solution all the time. However, it's very, very often and almost always needed to find the solution. Fibonacci is actually a special case where we only need two previous values at any subproblem, so instead of using a data structure, we can simply store those values in variables. This allows us to find the solution to any subproblem from just using the solution to the prior two subproblems. However, it's almost always going to be required to use a data structure in dynamic programming, so that should be the first thing you look to do, unless beforehand you just know it's going to be one of these special cases where you only need variables. But if you are able to remove the data structure, it can go from an O of n linear space problem down to a constant space problem because you're only using variables. The most common case is where you're going to need to use a data structure to store the answer to your subproblems. So what we see here is very in line with what you'll see in many dynamic programming questions. And one thing I want to stress is don't try to memorize these tables. You can't memorize them all, and it's not going to be the most effective way to study. To really understand the intuition behind dynamic programming, it's all about learning to think in subproblems. Think about solving all these smaller subproblems and then building up the solution until you reach the answer. So up to this point, we've only looked at the Fibonacci function. In fact, we've looked at it so much that you might be ready to punch a hole in your computer if I bring it up again. So let's move beyond the Fibonacci function and take a look at some other classic dynamic programming questions so we can really continue to build this intuition. We're going to start with the coin change problem, and this is actually one we solve in the course, and we'll go deeper on it, but it's good to take a look at now because it really moves us forward, and it's a good next step to see how we can start thinking in dynamic programming. So the way the coin change problem works is you're given a target value and here it's 8. And we want to find the smallest number of coins we can use to reach this target. We're also given the denominations that we can use, and here it's 2 and 3. And we're going to build up the solution to find the smallest number of ways that we can reach 8. And we're going to do that by finding the smallest number of ways to reach all the items going from 0 up to the target. So we start at 0, no coins can reach 0, and we're going to use a hash table for the memoization, and we just initialize the first value to 0 because no coins can ever reach 0. Then we move to 1. Neither of these coins can reach 1 because they're both larger. Then we get to 2. Well, we have a 2 coin, so this is the smallest number of coins we can use to get to this spot. Then we get to 3. Well, there's no combination with the 2 coin to reach a value of 3, but we have a 3 coin, so the smallest number of coins to reach 3 using this coin is 1, which is the 3 coin. And then we solve for each of the values for 2 and 3. We memoize the smallest number of coins to reach each spot, and in each case, it was 1. Then we reach a value of 4. We want to see if any combination can reach 4, and we try it with each denomination. So we check 2, and what we do is subtract 2 from this value to see the smallest number of coins to reach a prior spot. So we're looking backwards or checking the solution to a prior subproblem. We saw that it was 1, and we know we can use a 2 coin to reach 4. So we use 2 coins, so the minimum number of coins is 2. We subtract 3 from 4 to look backwards. That's 1, and we didn't have a way to reach the 1 spot, so we can't use 3 to reach the value of 4 with any combination of coins. Then we move to a value of 5. We try it for the 2 coin, so we subtract 2. We get to 3, and we saw the smallest number of coins to get to 3 was 1 coin, so we add another coin to that to get to 5. And then we also check it with the 3 denomination. We subtract 3, get back to 2, and here we see we had the 2 coin, and we can add 3 to that. By using the answers to previous subproblems, the optimal answer was 2 coins for both. So we memoize 2 coins. Then we get to 6. We subtract 2, which brings us to 4. We could get to 4 and 2 coins, so by adding 2, this is 3 coins. We try for 3. We subtract 3. We could add 1 and 3 to the prior coins, so we got there in 2 coins. So then we memoize 2. We do this again for 7, and then for 8. And then once we solve the value for 8, this is the solution to the problem. So what we did, we tried all the options at all the points to build up the solution. And along the way, we memoized the number of coins to get to each spot, and then for each subproblem, we looked backwards to see how to reach each current spot by adding each denomination to the solution of a prior subproblem. So even though this question may have seemed complex at first, all we did at each point was try all the possible items for each value, and then kept the best solution at this spot. And then we built up the solution by trying each additional item and solving its subproblem. We found the optimal solution to each subproblem by using the optimal solution to previous subproblems. And this is really the fundamental thought process of dynamic programming. So each subproblem is a decision. We have a choice to make, and we make the optimal choice at each point by using the current value and then the previously calculated subproblem solutions. Another classic dynamic programming question is the knapsack problem. And what it says is you have a knapsack that holds a maximum weight, and you want to find the combination of items that has the largest value that stays below this maximum weight. So you're trying to balance this weight and the value to find the optimal solution. And again, we're going to use a data structure to store the answer to subproblems and build up the solution. And I want to stress again, you shouldn't be memorizing. The key to learning dynamic programming is thinking in subproblems. You go through all the subproblems, trying all the possible values, and then you calculate the optimal solution at each point. So to find the optimal solution at each step, we use the current input value, and then we use the answers to previous steps, which is the optimal solutions that we calculated for the prior subproblems. And the way we solve the knapsack problem is by trying all the items at all the possible weights. So we start at 0 and then solve the subproblem of finding the best value that fits inside each weight until we reach the maximum weight. So we start with item 1 and check its weight against all the possible weights, and since it has a weight of 5, the only place it can work is this last spot for its value of 60. Then we move on to item 2, and we go from 0 up to the max weight again, and then once we reach 3, this is the item's weight. We see 50 is greater than 0, which was the previous solution to this subproblem, so now we store 50. Then at a weight of 4, it again fits inside this, 50 is greater than 0, so now we store 50. But then at 5, a previously calculated value of 60 is larger than the 50 that item 2 would add, so 60 is still the best solution at a weight of 5 when we consider item 1 and 2. Then we move to item 3. It weighs 4 pounds, so once we get to a weight of 4, we see that 70 is greater than 50, the previous solution to this subproblem, so we replace it with 70. Then, at a weight of 5, the weight of 4 still fits inside this, and 70 is larger than 60, so we replace this value as well. So what we're doing at each point is just making the optimal decision based on the value, and then the previously calculated answers to each subproblem. And then finally, we try item 4. It weighs 2 pounds, 30 is greater than 0, so we keep 30, 30 is less than 50, so we keep 50, 30 is less than 70, so we keep 70, but then when we get to 5, since item 4 only weighs 2 pounds, we can sum it with the previously calculated value, which is 50, because a weight of 3 plus 2 equals 5, so both items can fit in the knapsack. So we add 30 to 50, which gives us a value of 80, and this is also the end of the problem. We tried all 4 items with all the weights, and we always kept the best weight at each point, and then we combine them as we move forward, either trying to add it to previous weights or checking if the current value is larger than a previously calculated value at that point. So each point is a decision, and we always make the optimal decision based on the information that we have. And then, when we solve all the subproblems for all the possible values, when we reach the end, this is also the solution that we want. So once we solve that, we get the overall global solution to the question. And we did this by combining the local answer to all the subproblems. And in this case, we solve for a max weight of 5. The highest value is 80 by using item 4 and item 2, which also sum to a weight of 5. So at this point, you probably think I sound like a broken record. I keep repeating the same points over and over. And the main point is that dynamic programming is just an optimization where we get rid of duplicate work caused by overlapping subproblems by using memoization. So let's summarize the concept of dynamic programming. First, we must be able to solve the problem by breaking it into subproblems. To use dynamic programming, these subproblems must be overlapping. And when they're overlapping, we know this means there's duplicate, repeated, unnecessary work. And each subproblem is its own decision, and you make the choice that will find the optimal solution at each step. So you take the input for that step, and then the optimal solution from previously solved subproblems to find the current solution. We use memoization to store the result for each subproblem, so when they're overlapping, we don't perform the same calculations again. We just use these previously calculated values and don't perform this duplicate work, and this allows us to find the best answer to the current subproblem. Then, after we solve all the subproblems locally, we continue to build up these solutions until we reach the end. Then once we're finished solving all these subproblems, we'll also have the global solution, and this will be the answer to the problem. And that's dynamic programming. Thanks everyone, and I'll see you in the next lesson.